All right, so class. So we're going to do a lab on Coulomb's law, and you can find the link in the module. And when I tried it, it didn't actually work for me when I clicked the link, but it didn't work in Canvas. But then you can just open it up as its own web page, and it should work fine. Okay, so we're going to be looking at Coulomb's law, where we have this just looking at the forces between these two charged objects. So we can do a few things here. We can move the charges around. Wait, it should, so when we start this, should have started from the beginning. Yeah, we want to click on the macro scale, and then that should bring us here. So we have two charges, we can move them around, and you can see the force on each charge. Like here, you can see they have the exact same value, and these arrows give the directions. So in this case, Q1 is negative and Q2 is positive, so you can see they're attracted to each other, and same magnitude of charge. So let's bring up Coulomb's law. We have Coulomb's law here. F equals our constant times the product of the charges divided by the distance squared. So basically, we have three variables. Ke is a constant, and our variables are Q1, Q2, and R. And but Q1 and Q2 are kind of exactly the same in this formula. They play the exact same role. So we're going to do two experiments on this website. So the first thing we're going to do, part A, wrote that here, is we're going to vary one of the charges. So I wrote it, this is just Coulomb's law, but written in a particular way. So we're going to fix everything except for one of the charges. We're going to vary one charge and then measure the force. So for this, our data that we're going to have is Q2 and F. And we're controlling Q2. And then we're going to measure the force. So Q2 is the independent variable, and F is dependent. The force depends on charge Q2. Okay, so it's a good idea to have in mind what we're actually, what our actual data is, because we have three variables. But Q1 and R are going to be fixed in this experiment. So let's bring up the lab. What I'm going to do is I'm going to move, actually in this case it doesn't matter. Let's say Q1 is at 3, Q2 is at 7. And again, we're measuring from the center of the charges. So you'd get a pretty different answer if you measured from one end of this charge to the closest end of the other one. So we want to measure from the center of one charge to the center of the next. And we're going to keep this distance fixed throughout the entire trial. So I think what I'll do is I'm going to leave charge 1 alone, and I'm going to start charge 2 at negative 10 microcoulombs, and I'm going to leave this distance 4 centimeters fixed. So let's write that down. We have Q1, Q2, just Q1 and R. I'll just do that. So again, we're not doing any calculations. You don't have to write it down in a spreadsheet, but you definitely want this information in your lab report. Okay, so again, for part A, these two are going to be fixed, and our data is going to be Q2 and F. So if we're going to plot this, Q2 is the independent variable. We'd have Q2, which is in microcoulombs, and then we'll plot the force in newtons. The dependent variable would be, on the y-axis. Okay, so that's what we're going to do. And we're going to start out. Let's make a table Q2 and force. And Q2, we start at minus 10 microcoulombs, and we're going to increment, one at a time. Now, it's better to, considering to flip back and forth. Yeah, we're going to have a lot of data, but why not? I guess we could go fewer points, but it's a pretty quick process because all we have to do is to get data. Let's start here. They're 4 centimeters away. Q1 is fixed. We're going to leave this alone. And right now the force is 224.689. Now, one thing we're going to find is that there's no errors in this lap, which is a bit unfortunate. So to kind of keep our numbers from being completely perfect, I'm going to round it off to, like, say, 224.7. And then, we'll just click this arrow to change it to minus 9 microcoulombs. So that'd be 202.2. And we can do that. So all it takes is a click. And if you just write this out on paper and then transfer it over one time, it'll, go pretty quickly. So yeah, I think I'll do that. 179.8. 157.3. And then almost up to 0. Yeah, see, the force here for 0 is exactly 0. So that's a little unfortunate that there's no errors introduced in any. I kind of wish they built in where you could, like, if I try to move Q2, which don't do this in your lab, but it kind of moves in little jumps, so it's easy to line it up perfectly. It'd be nice if you could move it through finer increments so there'd be at least some measurement errors. But it looks like things are going to be pretty exact here. And then if we go to 1, 22.5, that's exactly what I had before. And but look at the arrow. Now it's attracted. So, like, these are basically negative values. So if we go back to, like, say, negative charge, and again, it's like this because charge 1 is negative. So if charge 2 is negative, we're looking at the force on charge 2. And, that's to the right because they're repelled from each other. But then if we make Q2 positive, then it's going to be attracted. And so we should enter these values as negative. But we're going to get the exact same values. So I'm just going to make this table, filling in these numbers. And then these numbers are going to be negative, which we want to include. We want to include that minus side. Okay, so a lot of data, but it's a pretty quick process. And then going back to the picture, remember we want to plot the force as a function of the charge. So, yeah, if we highlight this, the charge will be on the x-axis, force on the y. And again, just insert chart. And then we go with XY scatter. And I'm just going to hit finish. So we get this very nice line that goes through the origin. And yeah, it's downward facing because I picked Q2 to be negative. So if we have negative charges, then the force would be positive because they'd be repelling each other. The force on Q2 would be the right to the right. So that's why this is negative. If we picked Q1, positive, then it would be an upward slope. But really, in the end, we just want the value of the slope. So I'm going to click this data, insert trend line, and you go with linear equation, and all I want is this slope minus. I'm going to write this down on paper. So this is 22.469. I'm going to write down that number. I don't want this cluttering up the graph though, so I'm going to actually delete that. So I have the actual value. And again, there's only one set of data here, so I'm going to delete that. And we can do all the same stuff as before. Format data series. No, I'm not going to do that. We can make these smaller. It's been a while since we did the last one, but I thought it was this actually. Oh yeah, so here we can select a different type just to make it look a little nicer. Something more circular and make it a little smaller. So it looks more like data points. Actually, yeah, I deleted that line. I actually do want the line, just not the equation. So I actually deleted the line as well. So let me highlight these data points again. Yeah, it's a little tricky to get the chart has all these elements and it's not always sure what you're clicking on. Okay, there we go. So I'm going to see if I can insert the trend line. Okay. So now we just have the line with no equation. So I already wrote down the slope, which I'm going to write over here. The slope is 22.469. Now we know the slope is negative, but we just want the value of the slope. Because, we could have looked at the force on Q1 and then it would be, an upward slope, but the exact same values. So we get the exact same value either way. So we just want to look at the magnitude here. And ultimately, what we want to do is find our constant K. So if we look at the slope, when we have to include axes as well. But here, let's just go back to this one. Remember, the force is in newtons and the charge is in microcoulombs. So our slope has units of newtons over microcoulombs. And let's go back to our equation again, and we can see our slope is here as well. So our slope is equal to KEQ1 over R squared. And now we have our slope. Let's just call that M for now because we're not using M for anything else. That's known. This is 22.47, I'll say, newtons per microcoulomb. So again, units are very important. And we know that's equal to KEQ1, which is 4 microcoulombs. Just put a positive 4. And then R is 4 centimeters, so we can plug that in. Now, your Q1 and R might be different. You can pick whatever you want. Just once you pick it, leave it fixed. And so you can put all that together and solve for KE. So that's our goal for part A. We look at how the force depends on the charge. All right, so I'm going to erase most of this. Let's just pretty much get rid of it. All right, and now let's look at part B. We're going to do something a little different here. So I'm going to rewrite Coulomb's law. So in this experiment, what we're going to do, let's bring this up. I'm going to bring Q1 all the way over to the end. Q2, let's leave it 5. That's fine. And we're going to start out, let's put Q2 at, say, 2 centimeters. And so what we're going to do is, I'm just going to write these down once and then move it over onto the spreadsheet. So I have fewer data points here, but, okay, so if they're 2 centimeters apart, this is 449.4 newtons. And I'm going to write down Q1 and Q2. So this is minus 4 microcoulombs and 5 microcoulombs. Okay. And in this case, we can see, force on Q2 is to the left, force on Q1 is to the right. Let's just look at the magnitude of the force here. Okay, so then we move Q2 to 3 centimeters, and the force decreases. 199.7, and then 112.3. All right, so almost done here with data. Okay, so I've got data, so I'm going to bring up the spreadsheet. And now we're going to plot force as a function of distance. So I'm basically going to delete this plot. Don't delete yours, because you'll want to include that in the report. But, I'm not even done with this because you definitely want to give it a label, and you really want to label the axes and include units. So we'd have to have an x-axis here. We could label that. And again, we've done this before in the first lab, so I'm not going to redo that part. If you don't remember how to do that, you can just watch that part of the first lab again. But, yeah, so for your graph, you want to look nice, so label the axes. And then take a screenshot, I guess, when you're done. You could, a good way to do that is you could use that, there's that tool. I know Windows has that. Well, like every computer, you can take a screenshot of your entire screen and then just crop everything else out, so you're just left with the picture. There's all sorts of ways you can just save something that's on your screen. I think you could probably just right-click on this and say, save, if you click on it right anyways. Or you could do copy, and then open a Word document and paste it in there, and then, save the image that way. But yeah, lots of ways to do it. So I'll figure you can find some way to get it from that screen to your lab report. So just, before you delete it, if you're going to, make sure everything is done. You have your axes and they're labeled and include units and so on. But now let's go for this plot. So I'm going to go back to the main thing here. So like we're measuring from 0. So we're just plot like we're recording the just the position of Q2, like 2 centimeters, 3 centimeters, up to 10 centimeters. And that worked, the R is a distance between the two charges. But I set up Q1 at 0. So like right now they're 2 centimeters apart. So this reading for Q2 gives you the actual distance between them. But if if Q1 was at any other location, that would be very different. Well, I mean, not much. We just have to subtract it. So I want to be clear on that. So I'm going to write down the values I had. And again, yours will probably be different. You can pick whatever you want for your charges. Oh, anything they let you pick anyways. All right, so here's the data. And this should give us an inverse square law, so let's see what we get. Insert chart, XY scatter. And yeah, we can see it looks like an inverse square law. So again, I like having just data points, not these huge. Let's see. No, not all that stuff. There we go. Yeah, now like these big symbols, but just and again, we can delete this. If I click on it right, we can delete it. There, I got that. Okay. So again, for your chart, you always want to label it. And again, not like a generic label, like not force as a function of distance. Try to, like, what are we doing here? What are we trying to do? We're plotting, like examining, the dependence of force on distance or something like that. Give it a name. And we're just going to have data points here. But again, label your axes and include units. So we're going to want a plot of the actual data. Actually, I wonder if we can do let's insert a trend line. I think a power will work. No, it only does positive exponents. So if we do a power, we can't make it a negative degree. Yeah, I don't think we can do like an inverse square one. Now let's try this and see what happens. Oh, okay, that worked out well. Okay, so yeah, you can include a fit to it. Okay, but this is clearly not linear. And what we want to do, again, is let's go back to what we have here. We want to find KE from this data as well. And then we'll have two values for our constant, which we can compare. So what we want to do after getting that plot is we want to linearize the data. And I'm not going to actually do that because we did that before. You should be able to figure that out. Of course, if you can't figure it out, ask, just ask in class or email. I don't mind helping, but, try to figure it out. And there's no big hint right here. Like, we fixed Q1 and Q2. So these are constant. And so try to figure out how to linearize the data. And then from the slope of that best fit line, you can find K for, for part B. So then the last part of the lab, what we're going to do, again, whenever you make a plot, give it a label. Make sure to label the axes and include units, all that fun stuff. But what we're going to do at the end is we're going to make a table. We're going to have K. I'll just call it K instead of KE. So, let's say KA is K from part A of the lab. Let's make a table. And of course, K has units. You want to get those out of the data as well. Back to brush. Okay. So yeah, we want KA. So this is your, yeah, that's a horrible B. I can't live with that one. I'm going to have to redo it. Okay. So this is your value of K from part A. This will be your value of K for part B. So you write these numbers in here, and then we have the percent difference. And it's a percent difference. Yeah, let's do both actually. So we're going to have two tables. Yeah, let's have one here. So we measured K in two different ways. And you know what? I'm going to have to rewrite a little bit on the... Yeah, I think a better way to do this. Let's say we have KA, KB, and then let's take the average of those. Now, these two values should be extremely close to each other, especially because we're doing a fake lab that does not have errors. So, yeah, we should be... I haven't actually gone through and gotten, best fit line for the second part. Maybe you won't have any errors at all. Maybe they'll just be exactly equal to each other. I wouldn't be surprised at that. But we also have our K value, the theoretical, or not even the accepted value. So let's also make a table for an experimental value, which is your average value. So like these are both, like here and here, these are both experimental values, but just take the average and put that here. So here, this will be K average. And then we have our K theoretical. That's at 9 times 10 to the 9th Newton meters squared over Coulomb squared. And then let's take the percent error. And I'm going to call it an error this time because the that 9 times 10 to the 9th value, that is known, very accurately. And if we were doing an actual lab, it would be our result that would be off. So we're comparing it to something that is known. So we'll call whatever we get, whatever difference we get, we're just going to say that was the error on our part. So yeah, percent error would be the right way to do it here. So like the formula, you take the difference of the two values and then divide by the theoretical and then convert that to a percentage. So yeah, that's basically it. This lab I think is a little shorter than the other one. So we're going to measure K in two different ways and get an experimental value by taking the average, compare that to theoretical value, and find the percent difference. So this lab shouldn't be too long. And make sure, just you include everything you need. So you should have, like all the data, like tables of data. You want to include those. And also you should have 3 plots. One from part A, where you just have the force as a function of charge, the charge Q2. And in part B, you should have the force as a function of distance, and then a linearized version, because that relation is not linear. So you want to linearize it so you can get a best fit line and then use the slope. So that's the idea for this lab. So yeah, we're doing, I'm doing a little bit less in this recording than last time, but last time I spent a lot of time talking about graphs, and hopefully, hopefully you'll be able to get that part since you've already done it. And if not, if there's anything you don't remember how to do, you can just go look at that one again. And you can always ask questions. So, let me know if you have any issues with any part of this, and then, we can talk about it in class, or if you email me, I can reply that way. But, I think that'll be it for this.